Hi, welcome back. In this video we're going to look at something called a Smith chart, which actually can help us design transmission lines and solve transmission line problems. The Smith chart is actually kind of strange to look at, and so in this video we're going to look at the derivation and the theory behind the Smith chart, and then in future videos we are going to apply them to some examples. Okay. So Smith charts are graphical representations of transmission line quantities such as the reflection coefficient, the input resistance, and the viswar. So these are three things that you can determine from a Smith chart. And in the old days of slide rules and abacus, the Smith charts provided a means to calculate these quantities. And of course, we don't use slide rules and abacuses anymore now, and now software does these types of calculations. And so now actually Smith charts have a place in electrical engineering. They're used for the design of radio frequency systems, and they usually come standard in oscilloscopes and software packages. So really when you're designing a circuit, when you're building a circuit, you can probe the circuit, and the oscilloscope or the software will plot a point on the Smith chart, and you have to be able to then, as the engineer, know what that point on the Smith chart is telling you. And so then you would make design corrections or whatever you need to do. But so you need to understand what that point on the Smith chart is telling you. So let's look at how the Smith chart is constructed. I have these figures over here, and I don't want to address those figures just yet. Now, remember that the impedance of the line is related to the characteristic impedance, or sorry, the input impedance of the line is related to the characteristic impedance Z naught. And the idea is that we don't want to have a bunch of Smith charts for different Z0s. And what we're going to do then is normalize impedances, and we're going to normalize the characteristic impedance to unity. That is to say, and I'm gonna draw this as lowercase, and I'm gonna represent my lowercase without this dash going through the z. So this is a lowercase z0, meaning normalized characteristic impedance. And so what we do is we just take the characteristic impedance and we normalize it to the characteristic impedance. That is to say, all of our lines, no matter how they're constructed, are going to have a normalized impedance of 1. Normalized, so this would be the normalized characteristic impedance. And so what we're going to do then, so we can compare apples with apples, is we're going to normalize all of our impedances relative to the characteristic impedance. So the next thing we're going to do is we're going to take the load impedance, and so again this is lowercase z, meaning a normalized load impedance, normalized load impedance. We're going to take the actual load impedance and divide it by the characteristic impedance of the line. And so this will not give us in general unity, this will give us something, and it's going to give us possibly a real part and an imaginary part, and so I will represent that as R plus Jx. The R stands for resistance and the X is for reactance. Okay, now let's see how the reflection coefficient changes then from this normalization. So gamma, which is defined as capital ZL minus capital Z0 over capital ZL plus capital Z0, right? Now, if I divide everything there by Z0, okay, and if I do that to the numerator and the denominator, then gamma does not change. So I don't need like a different gamma here. Okay, this is still the same gamma. I'm not changing that. So this would become lowercase z, right, if I divide everything by z0, minus 1 over lowercase zl plus 1. Now, in general, that's a complex number, and so I can write it in rectangular form like I did up here, or I can represent it in polar form. So I can do this. It has a magnitude and it has a phase, right? Or I could express this in rectangular form using Euler's relation, and I'm going to call this gamma r for real part plus j times gamma I for imaginary part. So this is the polar form. Okay, and this is the rectangular form. And I have not changed gamma here. We did the same thing to the numerator and the denominator, and so the gamma is the same as it's always been. Now, I'm going to manipulate this equation a little bit, and I'm going to solve this for lowercase zl. So I'm looking at this quantity here and this quantity here. So if I cross multiply, I have zl minus 1 equals zl times gamma r plus j gamma I plus gamma r plus j gamma I, like that, cross multiply. And further, then this would be zl times 1 minus gamma r, so I'm factoring out the zl because that's what I want to solve for. Okay, and then I've got lowercase zl is equal to, so if I divide, I've got this thing here. Okay, now that, again, we're saying it has a real part and an imaginary part. So that's the resistive part plus the reactive part. Okay, so now what I want to do is find those quantities. I want to find the real part of this thing, and I want to find the imaginary part of this thing. So one trick that when you're presented with a fraction of complex numbers in rectangular form, one trick that you can do is multiply both the numerator and the denominator by the complex conjugate of the denominator. So the complex conjugate is 1 minus gamma r plus j gamma I. So I'm going to multiply everything by that. 1 minus gamma r plus j gamma I. 1 minus gamma r minus j gamma I, like that. So I haven't changed anything there, doing the same thing to the numerator as the denominator. And so what happens when you do that, then in the denominator you have a purely real number. When you take a complex number times its complex conjugate. So in the numerator, I get this. And in the denominator, again, I get a purely real number, no j's. Okay? And so now we can see that the only j is right here. So this is the imaginary part, right? And the rest is the real part. So now we can see that r is equal to 1 minus gamma r squared. So this is the resistive part. Like this. Okay, that's the resistive part. And then the imaginary part, or the reactive part, is what I've circled in green, minus the j. Okay, like that. No big deal there. All right, so let me erase some of this. Now, with some algebra, we can work this out by completing the square and so on. To this for the resistive part, and for the reactive part, we can do something similar and get this. Okay, so now we want to figure out, okay, well, what is this telling us, right? And so I want to remind you that the equation of a circle is x minus x0 squared plus y minus y0 squared plus r squared. Okay, and so this circle would have a radius of r and be centered at x0, y0. So we compare that to our first circles here, the resistive circles, and we see that these guys have a radius of 1 over 1 plus r, okay, and they're centered at r over 1 plus r, comma 0. And remember, the r does not stand for radius here. The r stands for the resistive part of this thing. And we look at the x circles, the reactive circles, and we see that the radius is 1 over x, and the center is 1 comma 1 over x, right? If we that is to say, if we plot these circles in a plane where the horizontal axis is gamma r and the vertical axis is gamma I, real versus imaginary part. Okay, so and that's what I've got over here, and that's coming up in a second. Okay, so now that we understand that, let's look at an example. Let's say, for example, like a load impedance. Let's say we have a load impedance capital, so before it's normalized. So this is an example. A load impedance of 50 plus J25 ohms, and that's terminating a transmission line that is characterized by 25 ohms. Okay? Now, in this case, the normalized load impedance, so lowercase zl then, would be zl divided by z0, and so that would be 2 plus j. All right? And remember, that's r, the resistive part, plus j times the reactive part. So we see then that the resistive part normalized is 2, and the reactive part normalized is 1. So in this case, then, we can compare what we just set up here about r, and the center and the radius and so forth, and we see that yes, so r is 2 in this example, and x is 1, and so the resistive circles will have a radius of 1/3, 1 over 1 plus r. So the radius is 1/3, and the center of the r circles would be or the r circle, I guess, would be 2/3. R is 2, 2/3, comma 0. So we have, again, for this particular example, we have a circle, the r circle, has a radius of 1/3 and center at 2/3, comma 0. Now, the x circle, the reactance circle, then would have a radius of 1 over 1, and a center of 1 as well. Okay, so we have two circles there. We have the r circle and the x circle. Now, in general, or I guess not in general, but for more cases, I'll give you a couple cases, and I'll put more in my notes. But let's say the normalized resistance So this is the R value. Let's say the normalized resistance is 0. In this case, the radius would be 1, right? If you go by 1 over 1 plus 0. And the center would be 0, comma 0. So you can see how these circles are being defined now based on, again, the unnormalized load impedance and the characteristic impedance of the line. All right, and let's look at another one. Maybe the normalized resistance is 2, and then in that case, if you plug R is equal to 2 up here, you'll see that we have a radius of 1/3 and a center at 2/3, comma 0. I guess that's what we did here. Also, we can have infinity, right, an open circuit, and if you plug in infinity up here, you'll see that the radius is 0 and the center is 1, comma 0. That's an interesting case, and I'll say more about that in a second. Now let's look at the X circles then for this case. So we can, or for these cases, normalized reactance. Okay, so if we have a reactance of 0, we can plug it in now here, and we see that the radius would be infinity, and the center is at 1, comma infinity. That's an interesting case. And again, I'll say a little bit more about that in a little bit. Also, if we plug in plus or minus 2, notice that the radius will be 1/2, right? Because you can't have a negative radius. And the center will be 1, comma plus or minus 1/2. Okay, the radius we're just saying is always going to be positive. And also, let's look at plus or minus infinity. In that case, the radius would be 0, and the center is at 1, comma 0. Okay, so that's also an interesting case to us. So what we can do then is we can take all of these cases, right, and we can start to make these circles. And so I want to direct your attention to the top left. I have in the very top left, so this here. Okay, these are the R circles. So again, I have gamma R as the horizontal axis, the real part of gamma, the reflection coefficient, and the imaginary part of gamma on the vertical axis. So here are the circles. So for example, we said these are the R circles here. So we said that when R is equal to 0, we have a radius of 1 and a center of 0, 0. So that would be this circle right here. Okay, it's centered at the origin and it has a radius of 1, so you can see that there. When R is 2, we said the center is at 2/3, comma 0 and has a radius of 1/3, so that's this guy here, right? Also, the interesting case here, when R is infinity, we said the center is at 1, 0 and it has a 0 radius, meaning it's just a point, so that's right here. Okay, so, and you can plug in more normalized resistances and get these circles, and they make this type of family or locus of circles. And we can do the same thing for normalized reactance, and so that is here. These are the X circles, excuse me. And the funny thing here, though, is that in the unit circle, these circles are not fully contained within the unit circle. In fact, their centers can be, away or out of the picture of the unit circle. And so I've got these circles shown in this figure, but you'll see they're not entire circles within that unit circle. They come out kind of, and they come back around. So I'm representing that with the dashed line, and only the solid part of those circles will apply. Because you see, then when we overlay the two figures, the R circles and the X circles, meaning we have a real part and an imaginary part, then this is what we get. This is the bottom left figure here that I want to show you. This is the overlaying of the two circles. And so this is what really matters for our chart. we want to figure out what is the normalized load impedance, so we find that point on the chart. Okay. So, and actually, this is just an abbreviated chart. I'll show you more detailed charts in the example problems. So, I want to point out a few things. For the R circles, notice that the centers all lie on the horizontal axis. That's the real part. The centers of the R circles all lie on the horizontal axis. Also, as R increases, the circles get smaller. Of course, right? As R increases, the radius goes down. So here's an R of 0, an R of 0.2, R of 0.5, R of 1, R of 2, R of 5, right? The circles are smaller, and R of infinity, the circle is just a point. All the circles pass through 1, 0, that's this point here. R is infinity at that point. Now for the X circles, notice that the centers all lie on gamma R equals 1. Gamma R equals 1 is here, this line here. So all of the centers of the X circles, although you cannot see the full circle, they all lie on that axis. Okay? Inductive reactants lie above gamma R equals the gamma R axis. So inductive reactance is positive J. So those are all of these circles. Capacitive reactance, negative J, those lie below the gamma R axis. So that's down here. As the value of the reactance, or the magnitude of the reactance, since it's imaginary, increases from 0 to infinity, the circles get smaller. So here's the magnitude increasing, and the circles are getting tighter and smaller, right? Same thing here. The magnitude increases from 0.2 to 0.5 to 1 to 2 to 5, and going to infinity, the circles are getting smaller. And the normalized reactance of infinity is at this point as well, 1, 0. So the Smith chart has the property that each R circle is orthogonal to each X circle. So each time there's an intersection there, they are perpendicular. That's interesting, right? Now, I also want to point out that you remember from previous videos about transmission line and the impedance on the line that the impedance repeats every lambda over 2. And so lambda over 2 will correspond to rotating around the chart 360 degrees. Once you move over lambda over 2 down the line, it starts to repeat like 360 degrees. So and usually on these Smith charts, clockwise represents moving towards the source, okay, and counterclockwise is to the load. So if you know that on the line somewhere you've got this impedance, input impedance, and then you want to go down the line towards the source, you can figure out how much you need to rotate to your new point to figure out what the new input impedance is. So again, lambda over 2 corresponds to 360 degrees. So if you go lambda over 4, that would be 180 degrees, and so on. So you need to set up a proportion there. And then it's not shown here, but you'll see it in the example problems. Usually 3 scales are around the chart, on the perimeter of the chart. The outer scale is used to find the distance on the line from the source in units of lambda. The next scale determines the distance from the load in units of lambda. And then the innermost scale provides the angle that your point makes. So this is useful for finding the angle of gamma. Okay, so yeah, like I said, let's take a look at some examples of how to use the Smith chart. Thank you.